Good afternoon. So I'd like to go over an example in today's lesson, which I really like because it's a very nice illustration of when one can actually need a Fourier series that involves both sine and cosine. Notice that at this point we had essentially two situations. We had Dirichlet problem in which you had prescribed values at the boundary points, and those led to Sturm-Liouville problems that had these type of eigenfunctions, which will lead to Fourier sine series. So you have just basically sine functions in the eigenfunctions, basically. Or Newman problems with prescribed values for the derivatives at boundary points that led to these type of eigenfunctions depending on the interval. And so this leads to the need to have Fourier cosine series. But we also learn that in some cases we also learn just Fourier series. So when do we need just Fourier series? I feel kind of weird when saying just Fourier series that basically involve both sine and cosine. So when do we need these type of series? When you identify the function by this type of summation, both sine and cosine. On some interval minus c and c. Now remember, for the Fourier series that contains both sine and cosine, the default domain is a symmetric interval around the origin. So here's the example that we'll deal with. It's the so-called temperature in a ring. So we have the heat equation in which the shape of the wire is in a ring. It's not that difficult, and I won't go over it, but it's not that difficult to show that the heat equation looks the same mathematically. So the object is a thin ring, a wire, for example, of negligible width, and heat basically flows along the ring in various directions, right? Again, according to the temperature gradient. So for example, if this is a cold point surrounded by higher temperature on the neighborhood, obviously the heat will flow toward that point. So imagine that the heat flows just like in a one-dimensional object, straight object. But in this case, the object itself is just a ring. So notice in this case, the notion of boundary conditions is not that clear what that could mean, or even if we need boundary conditions in the first place. Well, just to eliminate any suspense, we do need boundary conditions, but what those boundary conditions will entail. Presumably, if I told you that I know the initial temperature in a ring, so let's say I give you the temperature at all points in the ring, then what else will you need as conditions to describe the problem? Because then, you should be able to describe how the temperature flows from that point on as time goes on. Well, it depends on how you actually set up the domain for this, for the space coordinate, which identifies the position in the ring. And there is a way to actually identify the position in the ring that is basically leading in the end to Fourier series that involve both sine and cosine. So we'll probably write this down on the next page to start from scratch, because I'm going to make a mess probably on this first page. But the idea is, instead of, because there are many ways to identify the position in the ring. You can think about, for example, polar coordinates, but you could still use Cartesian coordinates in the following way. So let's say we have a ring of radius 1, and we're gonna identify basically the position in the ring. So basically the radius is 1, obviously then its length is 2 pi 2 pi times the radius, right? So the length of the ring is 2 pi. So to make it suitable for a Fourier series, you can basically choose any point on the ring. So let's sketch it one more time here. So I can choose any point on the ring and call it 0, the coordinate 0. So we can choose, let's write in words actually here. So we can choose any point in the ring and call it the origin, right? X equals 0. And to obtain eventually a symmetric interval around 0, let's say that we measure, the right half or the coordinates on the right half of the ring by positive numbers. So positive coordinates for the right half and negative coordinates for the left half of the circle, of the ring. And because the circumference, I should say the circumference, not the length here, but I hope you get the point. So because the circumference is 2 pi, the right half goes from the origin from 0 all the way to pi. And the left half goes with the negative coordinates all the way from 0 to negative pi, hitting the same point here. So this way I have my domain between minus pi and pi. So that will be the domain for the point that identifies the position on the ring. Now you may say, okay, but why do we need boundary conditions? Well, the boundary conditions now come from the fact that you must say mathematically, or you must impose mathematically that in fact x equals pi and x equals minus pi are the same point or the same location on the ring. So what you say basically is that at all times t, I must have the same temperature at x equals pi as x equals minus pi, and I must have the same flow of heat at x equals pi and x equals minus pi. Why the same? Because they are all the same location. That location is identified by 2 coordinates, right? Pi if you go to that point from the right side, and minus pi if you go from the left side. So the boundary conditions simply come from simply come as a necessity of how you actually identify these points by these coordinates. So it's important to understand that sometimes the boundary conditions don't come from physical requirements, but they come from a requirement that follows from your choice of identifying the points of the object. So because they are the same point, you must have essentially 2 boundary conditions. Like I said, at all points, if u of xt is the temperature, as we normally denote it, you must have u of pi t equals u of minus pi t, and then you must have the same flow, that is u partial x at pi t, the same as u partial x at minus pi t. So on the next page, we're going to write down the full problem with these conditions, and we get to solve it and see what we end up with. So stay tuned for the continuation. Okay, so the ring again with the conventions of notation that we had before for the coordinates. So the domain for x is minus pi and pi. So the heat equation is ut equals a squared. Here is xx. Sorry about that. So let me write it one more time. So the PD is u partial t equals a squared u partial x twice. And I forgot to write the initial temperature. So let's say the initial temperature is just a generic function f of x. I'll just write down at the end that you need the Fourier series for this function, because that's going to be the end point of it. So this is the initial temperature, and then the boundary conditions, like I said, are essentially of mixed type, if you want, right? Stating that the temperature at the points minus pi and pi and the flows must be the same because they represent the same location on the ring. All right, so let's move on with the separation of variables and see what we end up with. So as always, we know the drill already. We take the product form for the u of xt, plug it in into the PDE, so we get t prime, so big X times t prime equals a squared x double prime big T, and then we separate and we have x double prime over x equals t prime over a squared t, and then we introduce the separation constant lambda or minus lambda. Now let's see what the boundary conditions become. So we're gonna have x, so the first one, we have x of minus pi big T of little t should be equal to big X of pi big T of little t. Again, because we want non-zero solutions for any t, this leads to the boundary conditions x of minus pi should be equal to x of pi. Now you do the same for partial x of u, so that means x prime of minus pi big T should be x of pi big T, which leads to x prime of minus pi equals x prime of pi. All right, so the equation in T, I'm going to write it here because I'll deal with it a little bit later, is T prime equals minus lambda a squared big T, no other conditions for it. We're going to do this after I identify, of course, the eigenvalues. And the eigenvalue problem, or the Sturm-Liouville problem, will be x double prime of x double prime of little x. I'm not going to write of little x anymore. So plus lambda x equals 0. And the boundary conditions are x of minus pi equals x of pi. And then x prime of minus pi equals x prime of pi. So for so that I don't actually bore you too much, I'm not going to take into consideration lambda less than 0. We can show that it must be 0, just like in the previous eigenvalue problems we solved. Let's analyze what we end up with if we take the two cases when lambda is 0 or a positive number. So the first case is lambda is 0. And let's see if we end up having an eigenfunction in this case. So of course, if lambda is 0, the equation in big X is x double prime equals 0, which means big X of little x is a linear function in x, c1x plus c2. We integrate twice. Okay, so now let's pay attention here. If I plug in minus pi, so first of all, the easiest thing to notice is that the condition on x prime is satisfied no matter what, because x prime of minus pi is equal to c1, x prime of pi is equal to c1. So that's satisfied no matter what, because x prime is c1 for any x. But what about the other condition at x of minus pi equals x of pi? Well, x of minus pi equals x of pi gives me c1 times minus pi plus c2 equals c1 times pi plus c2. Notice c2 cancels, and if I rearrange the terms, this is 2 pi c1 equals 0, which means c1 is equal to 0. So in the case lambda is equal to 0, and I think I'm going to write it here to have it in this corner, we have an eigenvalue, right? So we can call the eigenvalue now is lambda naught. So lambda naught is 0. And the corresponding eigenfunction, which I can call it x naught, is actually C2, right? So if I show that C1 is equal to 0, that means big X is going to be C2. It can be any constant. Remember, for simplicity, just take that constant to be 1. Any non-zero constant will do as an eigenfunction. Remember, you can take it 1 because you're going to have a linear combination of these functions when we do the superposition principle. So lambda equals 0 is an eigenvalue, which corresponds to x naught equals 1, or any constant for that matter, for the eigenfunction. And now let's deal with the case lambda greater than 0. Remember, it's a good habit, if you prefer, to avoid square roots, to just denote lambda by alpha squared, or any variable to the power 2. Simply because you anticipate a square root when you deal with the solution in this case. You could do that if you prefer. I like to do that often. So if you don't do that and you keep lambda, you're going to have square root of lambda, which is not a big deal. So anyway, if lambda is alpha squared, the characteristic equation from the ODE here is going to be r squared plus alpha squared. And that gives you complex roots. So that means big X of little x is going to be a linear combination of, so let's say C1 of cosine of alpha x plus C2 sine of alpha x. All right, so here is the part that it's a little bit more subtle than before. So let's pay attention to the actual boundary conditions. The first one, x of minus pi equals x of pi, leads to C1 cosine of minus alpha pi plus C2 sine of minus alpha pi. That must be equal to C1 cosine of alpha pi plus C2 sine of alpha pi. Now, we should mention here that cosine is an even function, right? So let me write here in the top corner just to keep in mind. Cosine of minus x is cosine of x. That's, properties of trigonometric functions. And sine of minus x is minus sine of x. It's an odd function. So from this condition, these two are equal, right? Because cosine of minus alpha pi is the same as cosine of alpha pi. In the remaining ones, you can pull the minus out and move everything into one side, and you get 2c2 sine of alpha pi equals 0. That is c2 sine of alpha pi equal to 0. You might be tempted to conclude c2 is equal to 0, but let's not rush, because remember, alpha must be determined as well. So let's keep this for a moment until we deal with the second boundary condition. Because it's not clear whether you must have C2 0 or you must have sine of alpha pi equals 0. So let's do the other boundary condition, which is x prime of minus pi equals x prime of pi. For that, we need x prime of x, so we have to differentiate first the solution over here. So we have minus alpha c1 sine of alpha x plus alpha c2 cosine of alpha x. And now let's impose the conditions. X prime of minus pi equals x prime of pi. That leads to minus alpha c1 sine of minus alpha pi, alpha c2 cosine of minus alpha pi equals minus alpha c1 sine of alpha pi plus alpha c2 cosine of alpha pi. Just like before, cosine of minus alpha pi, cosine of alpha pi, these are the same, so you can cross them out. pull the minus out in the first one, so minus minus becomes plus. Move everything to one side. And alpha is not equal to 0. You're looking for non-zero, obviously, eigenvalues. So we get C1 sine of alpha pi equal to 0. So we're going to do the analysis on the next page so you can have a clean page. But keep in mind, at this point, we concluded that if lambda is greater than 0, if we're looking for a positive eigenvalue, then the resulting solution, the eigenfunction, is a combination of cosine and sine, and it must satisfy this condition. C2 sine equals 0, C1 sine of alpha pi equals 0. So let's analyze on the next page what this actually means in my case. All right, so let's see what we had about this eigenvalue problem. So again, we established that we have an eigenvalue 0 with the corresponding eigenfunction equal to 1. But for the case when lambda is positive, which we replace it by alpha squared for convenience, we had that x equals c1 cosine of alpha x plus c2 sine of alpha x. And the boundary conditions in this case were that c1 sine of alpha pi should alpha pi should be 0, and c2 sine of alpha pi must be equal to 0. So remember, we're looking for non-trivial solutions. So it's clear that we can't have, pay attention here, we can have both c1 and c2 0, because that'll be a 0 solution, obviously. So the only way for this to happen, these two conditions to happen, right, these two equalities, assuming that c1 and c2 cannot both be equal to 0, the only way for that to happen is to have sine of alpha pi equals 0, which means that alpha pi must be a multiple of pi, just like in similar other examples. And that means alpha must be n, which means the eigenvalue, which at this point we might as well call it lambda n, is equal to n squared, right? It's going to be n squared for n, 1, 2, 3, and so on. So we cannot have both of them equal to 0, but notice that we definitely can have either c1 or c2 equal to 0. So in other words, there is no reason to exclude neither cosine of alpha x nor sine of alpha x. So that is the key thing in previous example of Sturm-Liouville problems, because the way these constants were obtained, one of them, precisely one of them, either c1 or c2, must have been equal to 0. So for example, in the Dirichlet conditions, you had that c1 must be 0 and then c2 arbitrary, and you end up with sines. In the Newman condition, so in fact we can even write it down like this. In the Dirichlet problems, you had that c1 had to be 0 and c2 had to be not equal to 0, and that led to sine of alpha x, right, in the actual problem, so led to the Fourier sine series. In the Newman problems, then you had to have c2 equal to 0, c1 not equal to 0, and that led to cosine of alpha x. Now the difference is that here you could have either of the two. We can have either c1 not equal to 0 or c2 not equal to 0, meaning that we can't exclude neither cosine of alpha x nor sine of alpha x. Now, what does that mean? Well, it simply means that you have two distinct eigenfunctions for each eigenvalue. So that means when you have the eigenvalue lambda n equals n squared, the eigenfunctions in this case are given by cosine of alpha is n, remember, so cosine of nx and sine of nx. And as a matter of fact, we can use it even the same notation, because when you do the superposition principle, we have to assemble, of course, all of these functions. So you can write it like this: lambda n equals n squared, xn could be cosine of nx, xn could be also sine of nx for the same lambda n. And of course, in addition to that, let's not forget the one corresponding to 0. In that case, we don't have two versions. We have just x naught equals 1. So as you can imagine, this eventually leads to a general Fourier series, right? Because now when we go back, so we have to go back to the equation in T. If you remember on the previous page, so the equation in big T was T prime equals minus lambda a squared T. Lambda is going to be n squared. So the corresponding solution for Tn will be some constant an. We can actually take it, let's see, there's going to be a little bit of an issue with the notation here. Let's not do that right now, actually, because let's see, we're going to use basically two different notations for the constants. So let me just write it like that. So this is going to be just c, some constant c e to the minus na squared t. Because I want to use different notations for this constant c, since you're going to combine Tn with the two versions of the eigen functions. So basically the solutions you have at this point for the dependent variable u of xt, right, which is assembled as big X times big T, are the following, right? So you have, let's call this one, yeah, let's just enumerate them from left to right. So you have the one corresponding to lambda equals 0, right? So you have when lambda equals 0, well, when lambda equals 0, let's actually do this separately. When lambda is 0, that's going to be t prime equals 0. So t prime of little t is just a constant. And let's just call it 1, just like before, because you're going to have conditions, basically, I mean constants when you do the superposition principle. So when we have lambda not equals 0, one solution is going to be let's see, big X is 1, so that's going to be just 1 times 1, basically 1. And then when lambda n equals n squared, you have two pairs of solutions here. Tn is the same, e to the minus n a squared t. So that constant c, we can denote it by an, e to the minus n a squared t, times the eigenfunction cosine of nx. And the other version is bn e to the minus n a squared t times sine of nx. So what I mean is that this constant c that appears in the exponential when you solve for t, for each eigenvalue, you kind of have to use two different notations, because each solution for Tn is combined with the two different eigenfunctions corresponding to the same eigenvalue. So because the same eigenvalue gives you two different eigenfunctions, I'm going to have to use essentially two sets of constants, an and bn, when we assemble the solution when you combine it with Tn of little t. So now when you do the superposition principle, you have, and by the way, actually this constant for when t prime equals 0, just to keep the pattern here, you can call this one, you can denote it by a naught, basically, right? Not just 1, because then you have a linear combination of everything here. So superposition principle means that now you're looking for a solution of the form some arbitrary coefficient times the eigenfunction 1 plus summation from 1 to infinity these solutions. So an, because we can pull out that exponential, an cosine of nx plus bn sine of nx times e to the minus n a squared t. All right, so this is how the full solution looks like, a combination in both cosine and sine. And I'm going to finish here by noticing that the moment when you need, of course, Fourier series is right at the end when you impose the initial condition for the temperature, right? Where u of x0 equals f of x. Because when you replace t with 0, remember e to the 0 is 1, then you end up with a Fourier series. E to the 0 is 1, which must match the function given in the initial condition. So that means an and bn are the coefficients of the Fourier series of f of x on the interval minus pi in this case. So I'm going to leave it at that. And yeah, so this is essentially a typical example or a standard example, if you want, when you need a general Fourier series. In most of the other examples we're going to encounter, you need either the sine or cosine series, but this is an example when you need both. And let me conclude with a general remark. What you actually need in terms of a Fourier, in terms of a series representation, what you actually need at the end of the problem comes from the boundary conditions. That's why a small change can change the problem drastically in terms of what you need at the end. And as you will see in later chapters, the system of coordinates you have in the problem to begin with, that also may change the problem completely. For example, you need different types of series than cosine and sine. So that's it for today.